Hi, my name is Steve Blyle and I'm a welder. I learned to oxyacetylene weld over 25 years ago as part of an apprenticeship program, and today I operate a custom welding shop. While I use more modern processes like arc and MIG welding in most fabrication and repair, I still run into situations where oxyacetylene welding provides the best results for the job I'm doing. By definition, oxyacetylene welding is a process of fusion. Similar base metals are heated until they melt and the molten puddles are intermixed. When they cool, the pieces are fused together. In most situations, a filler rod of the same material as the pieces being joined is used to add metal to the molten puddle and build up weld bead. In theory, all metals can be oxyacetylene welded. In reality, it doesn't always work that well. The progression of an oxyacetylene weld is very slow, and the pieces being joined get extremely hot. This creates problems with metals like cast iron and stainless steel, and with aluminum, it's just plain hard to see the molten puddle because aluminum doesn't get red hot. For our demonstrations, we'll be using regular mild steel plate. Before we get started, I need to mention safety. Everything we'll be working with is going to be extremely hot. Don't get burned, and don't let anybody else get burned either. Wear protective clothing and avoid wearing synthetics. If they get burned, they melt to your skin. Use some good welding gloves, and safety glasses are a necessity. You also need to make sure your work area is clean. Move any flammable materials like solvents or paints away from where you'll be welding, and piles of sawdust, rags, or paper are real dangerous. Sparks can start these smoldering and you won't notice it. Hours later, it'll flame up and start a fire. Keep a fire extinguisher for all classes of fire available and know how to use it. In shops and on job sites, there's safety programs to help protect you. Even more, safety is an attitude. You need to decide to always work safely. As best you can, you need to try to know what you're doing and what's going to happen when you do it. Take your time, look up occasionally from your work, and you'll do fine. Okay, let's take a look at the equipment we'll be using. We'll start with the bottles. This is an oxygen bottle and an acetylene bottle. And these bottles come in different sizes and they can be leased or purchased. But if you do buy bottles, keep the paperwork, especially on the oxygen bottle. Over the years, so many of these have been stolen that some suppliers won't refill them unless you can prove where they came from. Of the two, the oxygen bottle is by far the more dangerous. These bottles are filled to over 2,000 pounds pressure, and if this valve is damaged or broken, this bottle is out of here like a rocket. And there's horror stories about that. You need to protect this valve. Not just for yourself, but for the guy filling the bottle and the next person that leases it. So when this bottle's in use, you need to have it chained up securely. And when the bottle's not in use and the regulator's off, or you intend to move the bottle, you need to use the protective valve cover, even if the bottle's empty. This is a pressure relief valve. If for some reason the pressure inside the bottle exceeds the limits it was designed for, this valve automatically releases gas until the pressure reaches a safe level. Acetylene is unstable at pressures over 15 pounds per square inch, so they use acetone inside the bottle as a stabilizer. As the acetylene is being filled, it's absorbed by the acetone, and this bottle needs to be straight up and down when in use. Also, acetylene bottles have a safety plug on the bottom, and if the pressure in the bottle gets too high, the plug blows out along with all the contents of the bottle. If this ever happens, move the bottle to a safe place when you can, but keep in mind that if it's not already burning, acetone and acetylene are highly flammable. Now, I was taught not to completely empty these bottles. With even the slightest amount of pressure left, moist air can't get in and contaminate the inside of the bottle. And whether in a portable bottle cart or up against the wall, these bottles need to be chained securely. This is real important. You can't be able to pull these over with the hoses or knock them over. That's a mistake you don't want to make. Also, both these bottles are regulated by the Department of Transportation and need to be straight up and down and chained securely when transported. These are the regulators. And before you mount the regulators, crack the cylinder valve a little to blow out any dust or moisture. And don't stand in front of it when you do that. On the oxygen regulator, the high pressure gauge reads up to 4,000 pounds and measures the pressure inside the bottle. The low pressure gauge indicates the working pressure coming out of the regulator. And this is a regulator adjuster. Screwed in increases the pressure, screwed out decreases the pressure. The high pressure gauge on the acetylene regulator only measures up to 400 pounds. And here again, this measures the pressure inside the bottle. The low pressure or working pressure gauge will be marked up to 15 pounds. Remember, acetylene is unstable over 15 pounds, and the working pressure for oxyacetylene welding will only be around 3 to 5 pounds. The regulator adjuster is the same, screwed in to increase, screwed out to decrease the pressure. Now, these notches on the acetylene regulator fittings indicate left-handed threads, and all the fittings on the fuel gas side of this equipment will be notched and have left-handed threads. This is to avoid mixing the equipment and getting an oxygen fuel gas mixture where you don't want it. Now, this equipment doesn't require any lubrication, and oxygen is an oxidizer. When combined with grease or oil, it creates an extremely volatile situation. This equipment doesn't require any oil, so don't use any oil on it. And if you do come across a regulator that is oily or greasy, don't use it. It may need to get sent to a technician for cleaning. Now, typically, you'll have a red hose for acetylene and a green hose for oxygen. And these hoses are usually combined to avoid twisting or kinking that might restrict the flow of gases. If you cut or burn these hoses, you can get repair parts at your local supply store, and they'll have a little crimping tool to make the repairs. 1/4 inch is a standard hose size, and I like to add a 15-foot section of 3/16 hose at the end. The smaller diameter hose is a little more flexible and easier to handle. Right here, I've installed flashback protectors. In case fire does head back down the torch, these stop it right here and keep it out of the hoses and regulators. This is a standard torch body. You have the main oxygen and acetylene adjustment valves. These are stainless ball seat valves, so when you close these, don't over tighten them. If you reef down on these, you can ruin the seats and the torch will start to leak. Now, the oxygen and acetylene aren't mixed in the torch body. They're mixed right here in the welding nozzle. And there's 2 O-rings here to seal the nozzle. So when you install this, just hand tighten the nut. Don't use a wrench, or you can crush the O-rings, causing the torch to leak at this connection. And I like to line the tip up with the valves. It makes it easier to make adjustments. Now, these welding nozzles or tips come in different sizes, and you can avoid a lot of problems by using the right size tip and gas pressures. So let's take a look at my chart. Welding tips start at 0.0 for metals thinner than 1/32 of an inch. That's like 22 gauge sheet metal, and there's an awfully small fire at the end of that tip. Notice that the same working pressures, 3 to 5 pounds, is used on both the acetylene and the oxygen, and the smaller tips all use the same pressure settings. I'm only showing tip sizes up to a number 4, and oxyacetylene welding is commonly used in this range, from about 18 gauge sheet metal up to 1/8 or even 3/16 metal. I use a number 1/0, a number 1, and a number 2 tip. And if you're only going to have one tip, a number 1 would be a good choice. Now, don't take me wrong. Oxyacetylene welding does work on thicker metal, and these tips are available up to a number 12 for 4-inch thick metal. But in reality, oxyacetylene welding is very slow. Also, keep in mind that any chart like this that shows a tip size to metal size is strictly a recommendation. When you go to actually weld, don't be afraid to try a larger tip or a smaller tip to find the one that works for you. There's a few more things on our list of equipment. You'll need some welding goggles. and this style fits over safety glasses. The standard lens is a number 5, and I use clear lenses to protect the filter lens. Now, the light from the torch isn't as intense as the light from electric arc welding. It won't burn your eyes the same way, but it's still pretty bright, and you can't see the weld puddle without a filter lens. Also, mill scale and other impurities can pop off the hot metal, and if the tip or the puddle gets too hot, it can pop, sending sparks flying. So good eye protection is absolutely necessary. You'll need a striker to light the torch. You'll need some tip cleaners and a good pair of leather gloves. Now, before we load this and fire it up, a lot of people wonder about using oxypropane for welding. While oxypropane burns at 5,200 degrees, which is plenty hot, the rate of burn is too slow. The heat's there, it's just not there fast enough to maintain that molten puddle that you need to weld. Okay, let's load this, adjust the regulators, and light the torch. Before we do anything, we want to make sure that both the valves on the torch are closed. Now, whenever you open any of these bottles, you want to stand back behind the regulator, not in front of it, just in case something does come apart. It's also a good habit to open the valves slowly, so the pressure doesn't hammer the internal diaphragms of the regulator. An oxygen bottle is a high pressure bottle, and high pressure bottles are open all the way. This valve has 2 seats, one to close the bottle and the other one to seal the valve stem when the valve's open. So open the oxygen valve all the way. Acetylene bottles are only open to 1/2 to 3/4 of a turn. In case something does happen, you want to be able to shut this bottle off fast. Also, use a bottle wrench, not a crescent wrench or a pliers, and leave the wrench in place when the bottle's open. For our demonstrations, we'll be using a number 1 tip with 5 pounds pressure. To adjust the regulators, you want the valve on the torch open. So open the acetylene valve on the torch and screw the adjuster in until you get 5 pounds. Then close the valve on the torch. And I'll do the same with the oxygen. I'll open the oxygen valve on the torch and screw the adjuster in to get 5 pounds here too. And don't forget to close these valves on the torch. Now, at some point, you need to check this equipment for leaks. A simple way is to close the cylinder valve and watch the pressure gauges. If the pressure stays the same, you're probably all right. If the pressure bleeds off, you have a leak. And you can find it by using a liquid leak detector like soapy water. Okay, our regulators are adjusted. We don't have any leaks. Let's light this thing. There's 2 things that need to be considered when adjusting the flame. First is the amount of gas that's flowing through the tip, and second is the relationship between the amount of oxygen and the amount of acetylene. Now, these tips are designed to operate with a certain amount of gas flow that helps keep the tip from getting too hot. With a tiny little flame, you won't have enough gas flow to have that cooling effect. And with a big flame, there's a chance you'll have localized overheating. Either situation can cause the torch to pop, which blows out the puddle. Now, adjusting the size of the flame isn't very difficult, but it is important. And with experience, you'll know by the way the flame looks, sounds, and how the puddle acts. If you're unfamiliar with this, a simple way is to open the acetylene valve a 1/16 to 1/8 of a turn, light the torch, and slowly increase the acetylene until the flame just about quits producing the soot or smoke. This amount of gas should come close to producing the right size flame. Once the acetylene is adjusted, slowly open the oxygen valve. You'll start with a long flame, and as you increase the oxygen, a small cone will appear right at the tip. The idea is to keep adding oxygen until the long flame and the inner cone come together to form a nice sharp cone. Let's see what this looks like. I'll open the acetylene valve, and I'll slowly increase the acetylene until it just about quits producing the smoke. Also, notice how the flame has started to feather out on the end. I'll start adding oxygen, and the cone will appear right at the tip. Keep adding oxygen until the long flame comes together to form a nice sharp cone. This is called a neutral flame, and this is what you want. If you add too much oxygen, it's called an oxidizing flame. Notice how the inner cone is thinned out and the increase in the rushing noise of the torch. Back to a neutral flame. If you don't add enough oxygen, the inner cone won't be sharp. And this is called a reducing flame. There's an excess of acetylene here. I'll add a little more oxygen, get back to a neutral flame. When I adjust the size flame on my torch, I like it right at the point where it makes a little noise. But regardless of the tip size or size flame you use, always adjust the oxygen and acetylene to get a neutral flame. Now, to shut this torch off, close the acetylene first, then the oxygen. That way the oxygen snuffs out the flame and fire doesn't go back down the torch. This is easy to remember because you turn the acetylene on first and you turn the acetylene off first. Now, when you've adjusted the torch to a neutral flame, if the inner cone isn't sharp or maybe it's angling to one side, your tip is dirty. Use the tip cleaners to dress up the face and clean the orifice. You need a clean tip to focus and concentrate the heat of the flame where you want it, and it does make a difference. Always keep your tip clean. I'd like to visit a little more about adjusting the flame. In welding, if the molten puddle comes in contact with the oxygen in the air, the metal will oxidize or burn. This will cause little pockets of gas, called porosity, to form in the weld bead. When the oxyacetylene torch burns, there's a chemical reaction between the carbon molecules in the acetylene and oxygen molecules from the oxygen, helped along by the heat of the flame. This chemical reaction produces carbon dioxide and purges air away from the molten metal. When you have a neutral flame, this chemical reaction happens just like it's supposed to. With a reducing flame that has an excess of acetylene, carbon molecules can be deposited in the molten puddle, making the weld brittle. An oxidizing flame with too much oxygen can oxidize or burn the puddle, possibly leaving porosity. So here again, always adjust the torch to a neutral flame. While we're looking at the equipment, let's shut it down, like when you're finished and rolling up for the day. We want to bleed the pressure off the whole system. Close the valves on both the bottles. Then open the acetylene valve on the torch first to relieve the pressure. When both the high pressure and working pressure gauges read 0, back off the regulator adjuster, so the next time the bottles are open, the regulators don't get hammered. Close the acetylene valve on the torch, and we'll do the same with the oxygen. Open the valve on the torch. When the pressure bleeds off, back off the regulator adjuster, and close the valve on the torch. Now I'm going to set this up again so we can try some welding. We'll try this welding with some metal plate that's a little over 1/16 of an inch thick. I'm using a number 1 tip, and we've already set the pressures at 5 pounds oxygen and 5 pounds acetylene. The whole idea of oxyacetylene welding is to use the torch to form a molten puddle of metal. And when you're welding, this puddle is everything. It tells you if you're too hot or too cold. You can see if you're penetrating, and when you add filler metal, you can see it tying in on the sides. You want to be able to understand what's happening with the puddle, and you need to be able to control and manipulate it. I'm going to start with just forming a puddle and moving it across the metal. I won't be adding any filler metal, just moving the puddle. Now if you notice, I have the metal blocked up off the table. This is so the heat doesn't transfer through, or I'd be trying to heat the whole table too. To start the puddle, move the flame down so the inner cone is about 1/8 of an inch off the metal. And keep the tip moving so you don't overheat one spot. I use a little circular motion here. Now this takes some time, so don't get impatient. Once the metal starts melting, keep the torch circling until the puddle is as wide as you want it. With this tip and on this metal, my puddle is about 5/16 of an inch wide. Then keep the torch moving in tight circles and make the puddle move across the metal. Watch the puddle now, not the flame. Watch the front end and the sides. You can see the surface impurities floating off the edges, and you can see the ripples forming behind the molten puddle. Depending on the joint and fit up, you'll sometimes be able to fuse pieces of metal together just by puddling across the joint. In most situations, you'll need to add filler metal to build up weld bead. If you noticed, I was angling the torch about 45 degrees in the direction of the weld. This angle is comfortable for me, and I can see to dip the filler rod into the puddle right under the flame. You can vary this angle a little, but if you get too high, the puddle tends to get real hot. And if the angle is too low, the heat just bounces off the metal. I'm going to fire this up again, use some 1/16 filler rod, and build up some weld bead. Make sure you get a good puddle going before you start to add filler metal. And remember to keep the inner cone off the metal. Once the puddle starts, dip the filler rod into the puddle right under the flame. Watch the front edge of the puddle to make sure it's melting, and watch the sides. You want to try to keep the puddle the same width. Keep the circles tight, and you can see the weld buildup on the back side. I've been using a circular motion, and you can also use a side-to-side or zigzag motion. After you dip the rod into the puddle and pull it out, keep it close to the flame so the rod's preheated. Whether you use a circular motion or a zigzag motion, you want to develop a rhythm, moving the torch and dipping the rod uniformly. Whenever you weld, you need to relax. Don't have a death grip on the torch, and don't hold your breath, or you can only weld a little bit. To finish this weld, you need to add some extra metal to the puddle, or you may leave a crater. Just circle the torch and dip the rod a few extra times. This looks pretty simple, right? So what can go wrong? Well, let's take a look at a few things that might help you out. The most common problem in oxyacetylene welding is that the torch pops, blowing out the molten puddle. If either the torch or the puddle gets overheated, it creates a situation where the gas is burning faster than the tip can deliver it, so it pops. Usually, this is because the torch tip is held too close to the puddle. You need to keep the tip up away from the metal. It can also be caused by using the wrong size tip or not having the flame adjusted properly. And don't be afraid to readjust the flame a little bigger or a little smaller. It might make a big difference. But make sure you keep a neutral flame. Make sure the gas pressures are adjusted correctly, and if you let the puddle get too hot, it'll pop. If you have a problem with the torch popping, look for a reason that it's overheating. When you start welding pieces of metal together, you need to get penetration. You don't want to just lay metal on top and hide the crack. When you start the puddle, you need to hang in there so the puddle will melt down into the metal. If you try to add filler metal too soon, you'll melt the rod with the torch and the filler metal will just lay on top. It'll get super hot and probably cause the torch to pop. You might be able to recover from this, but it's a lot easier not to start too soon. If you hang in there too long, you may just burn right through. And if this happens, let it cool down a few seconds, maybe clean it with a wire brush a little, and oxyacetylene welding works great for fixing those little holes. Most of the time though, if you hang in there too long, the puddle gets too hot, it'll start to bubble, sparks will fly, and the torch will pop. When you get the puddle going, the surface impurities will start to float to the edges. If you watch the leading edge of the puddle, some of these impurities will start to dance around. In TIG welding, we call this a dancing eye. This is an indication that you're getting some penetration, and you want to maintain this when you're adding filler metal. I dip the rod when the flame is at the back side of the puddle, and when I come around, I like to see the impurities dancing. This indicates that I'm getting uniform penetration. If that stuff isn't dancing around, I'll bring the torch around again before I add filler metal. When I weld, I'm a little more concerned about penetration than I am about building up weld bead. When you're done, if you don't have enough weld buildup, you can always clean it up with a brush and make another pass. But if you didn't penetrate, it's hard to come back over that first pass and get penetration. Filler rods come in 36-inch lengths in 1/16, 3/32, and 1/8 diameters. They're either bare metal or copper coated to help prevent them from rusting. Now, everybody wants some magic numbers as to what size rod to use with what size metal and tip. I'm sorry to say it doesn't really work that way. Every time you dip the rod into the puddle cools down, and you need to maintain the puddle. So ultimately, it's the heat of the puddle that determines the correct rod size. If the rod is too small, first of all, you won't be able to build up weld bead. But more important, the rod won't cool the puddle, and the puddle may overheat and pop. If the rod is too big, every time you dip the rod, the puddle will cool right down, and you'll have to get it going again. This will most likely produce a rough-looking weld with varying amounts of penetration. When you have the right size rod, you can maintain the puddle and add filler metal in a rhythm and make a uniform weld bead. The best thing you can do is to get different sizes of these rods, start small, and find the one that works for you. On our demonstrations, we're using new metal, but that won't always be the case, especially if you're making repairs. You need to clean any dirt, rust, paint, or grease off the metal. Now, an oxyacetylene torch does burn somewhere around 5,800 degrees, and that's hot enough to burn just about anything, but that's not the point. We're wanting to weld metal, not rust or paint, and any impurities on the surface will take the heat that should be going to the weld, and it'll slow down the weld progression. A big difference between a welder and somebody just learning to weld is that a welder will take the time to clean and prepare the metal. It makes the welding a lot easier and you can do a nicer job. Distortion or warpage happens because when the metal gets hot, it expands. And when it cools, it contracts. And it contracts more than it expanded. The hotter the metal gets, the more movement you get. In oxyacetylene welding, the metal gets extremely hot because the progression of the weld is slow, and you're putting heat to the base metals for a relatively long time. When the base metals cool, they contract and warp, especially on larger pieces of thin metal. Also, when the metal cools and contracts, there'll be a lot of residual stress along the sides of the weld. That's why the metal will break before the weld breaks. There isn't a simple solution to this warpage and stress. Let the metal cool slowly. Don't dip it in water or anything. And realistically, this won't be a big problem for the projects you'll be using oxyacetylene welding to do. Now, we've been demonstrating in the forehand technique. The torch is angled in the direction of travel, allowing the weld bead to cool and solidify. Backhand is when the torch is directed back towards the weld bead. The flame stays on the back of the puddle and the weld bead, allowing a maximum amount of filler metal to be deposited. This technique was mainly used on heavier metal. I think that the forehand technique is easier to use and it produces a nicer weld on the thin gauge metals that we're welding on. Okay, earlier we made a weld bead in the flat position. Let's have a look at the other welding positions. On a horizontal, we'll be welding across. You want to angle the torch up a little so the force of the flame helps keep the puddle up. Every time you bring the flame around, the molten metal will follow the heat down, but it won't follow it back up. This can give the appearance that the puddle sagged. When you add filler metal, dip the rod on the top side and watch the top side of the puddle to make sure you're leaving enough metal there. If you don't, you'll leave undercut. When you're starting out, try making small welds and don't try to build up too big of a weld bead. On vertical welds, we'll start at the bottom and weld up, and these are real easy with oxyacetylene. For one thing, the metal is preheated because the heat's rising, and the weld will progress a little faster. Now, if you can picture yourself turned on your side, a vertical is just like a flat weld. I know a lot of people don't want to believe that and think the metal will drip down, but it doesn't want to. As long as the puddle's not too hot, that metal wants to stay there. It likes the heat. Angle the torch up and keep the inner cone off the metal. Watch the puddle. It will tend to run a little hotter because the metal is preheated, and you may even want to try a smaller size welding tip. If you weld to the top edge, the base metal will be super hot. You can back the torch away a little and dip the rod a little more to help keep the puddle from getting overheated. If you have any trouble with a vertical, just start with the metal at an angle instead of straight up and down. And as you can get it, move the metal up steeper. Overhead welding is identical to flat, just a little more awkward. That molten puddle won't fall out. It wants to stay with the heat, unless you get too radical. Angle the torch in the direction you're going, keep the flame away from the metal, and wear some protective clothing, especially a hat. I like to cover my ear, because when you're up there welding, those sparks will go right down your ear, and you can count on that happening. Whatever position you're welding in, flat, horizontal, vertical, or overhead, watch the puddle. Move the torch, dip the rod, do whatever it takes to make the puddle do what you want it to do. When you get a little experience with this, all the welds will be the same no matter what position it's in, because you'll have control of the puddle. Now, every welder welds a little differently, and eventually you'll develop your own style and your welds will take on a certain appearance. But let's take a look at what makes up a good weld. On a good weld, ideally, you want the width and the height of the bead to be uniform. Now, this will come with practice, and while it's kind of cosmetic, it is an indication that the amount of heat put to the base metal and the penetration is also uniform. The sides of the weld bead need to be tied into the base metal, and the goal is to get 100% penetration. Now, in all honesty, it'll take a little practice to be able to get 100% penetration every time, but you do want the amount of penetration and amount of buildup to equal the thickness of the metal. If you don't run enough filler metal in, the weld may be below flush. And this can be fixed simply by cleaning it up with a brush and making another pass to build up weld bead. If you don't let the puddle penetrate enough, the metal will just lay on top. And if there's any kind of stress on this joint, it can work and it'll break. If the puddle's too cold or you're using too big of a rod and just gob some metal on, you can cold lap the weld bead. This part won't be tied in, and it doesn't do any good being there. It's also an indication that you didn't get good penetration. On a horizontal, if you try to carry more metal than you can handle, the weld can sag and cold lap the bottom side. Here again, this metal doesn't add any strength to the weld. Undercutting happens when the molten metal follows the heat away from the sides of the weld and you don't put it back. This isn't a big problem in oxyacetylene welding, but it can happen on horizontal welds and horizontal fillets. You always need to watch the sides of the weld puddle and make sure you're leaving enough metal behind. Now, we've been looking at making good weld beads. Let's see if we can use these to put some metal together. Basically, there are 4 types of weld joints: butt joints, lap joints, T-joints, and corner joints. Now, some of the most important factors in making a good weld joint are metal preparation and fit up. In most cases, it'll take longer to get the joint ready to weld than it will to actually weld it. Okay, let's start with the butt joints. When you're working on the thinner gauge metals, the edges will get extremely hot and melt away. So butt the 2 pieces tight together and tack weld both ends. A fit up like this can be fused together simply by moving the puddle along the seam. This produces a flush weld joint, and the strength will depend on how much penetration you get. If you have any concerns about the strength of the joint, add filler metal and build up weld bead. If the edges of the metal are uneven and there's intermittent gaps, you'll have to use some filler metal. If you try to fuse the metal together, bridging a gap with just the puddle, the weld will thin out right there. When you get to metal that's around 1/8 of an inch thick, you can leave a little gap. The edges of the metal will melt easily, and you want to build up weld bead over flush. For a strong joint, you want good penetration here. If you don't get 100% penetration, you can flip the piece over and run a bead on that side too. Once the metal gets up around 3/16 of an inch and thicker, it's harder to get good penetration with a puddle. You can bevel the edges so the puddle starts out deeper in the joint. This is about a 30 to 45 degree angle, and I like to leave about a 1/16 flat spot on the bottom to help carry the heat. Leave a little gap and just start filling it up. You'll probably need to make more than 1 weld bead to fill this over flush, so use a wire brush to clean it up between passes. And if the piece is small, you may want to let it cool down a little in between the passes. On butt joints like this, because we're welding on the top side, the pieces will warp up. You can stop this a little by welding on both the top and the bottom, but because oxyacetylene welding gets the base metal so hot, you'll always get some warpage. On a lap joint, this is called a fillet weld. You want the weld to come up and out a distance at least equal to the thickness of the metal. Keep the pieces tight together and tack both ends. On thin gauge metal, the top piece will melt back a little because you're putting the heat right to the edge. You need to pay attention to the top of the puddle to make sure you're not leaving undercut. This is a fairly common weld joint, and it's pretty simple. An exhaust pipe on a car or truck where one piece fits inside another and you weld around is a good example of a lap joint. A fillet weld is also used on a T-joint. This is kind of a combination of a flat weld on the bottom side and a horizontal weld on the top side. Angle the torch right into the corner, and you need to pay attention to the top side of the puddle. Here again, the weld should come up and out a distance equal to the thickness of the metal, and ideally, the weld should be crowned. If the weld is flat or even concave, you want the throat of the weld to be equal to the thickness of the metal. When you only weld on one side of a T-joint like this, these pieces will try to draw in this direction. Corner joints are my favorite, and there's 3 ways to make a corner. You can lap the edges and run a weld bead on the outside where they join. If you need more strength, you can make a fillet weld on the inside. On this one, you butt the inside edges together to more or less form a bevel. The edges of the base metal melt easily, and you'll have good penetration. If you can turn the pieces so the weld is straight up, you get a nice rounded corner. This type of corner seems to produce the least amount of warpage and distortion. On thinner gauge metals, you can lap one piece past the other a little bit, and this lap acts like the filler metal. You can just move the puddle up the seam, melting the lap metal and tying it into the other piece. The weld buildup depends on how much you lap the metal, and you can try a lap equal to the thickness of the base metal. This type of joint will produce an extremely smooth and uniform weld bead. Of all the different types of oxyacetylene welds you can make, this is probably the easiest. When you're welding on any of these joints, the metal is going to try to move because it's getting hot and expanding. So when you're fitting up the metal, tack both ends of the joint, and if you're working on long pieces, tack it several times along the seam. Try to avoid big gaps. They take forever to weld up and the metal will get really hot. When you leave a gap, try leaving about 1/16 of an inch and keep the gap uniform. Take the time to get a good fit. It'll make the welding a lot easier. I hope I've been able to show you a few things to help you get started oxyacetylene welding. If you get the opportunity, watch how other people weld too. I'm sure you'll see some different ways and hear some different ideas on how to do this, because while we're all looking at the same thing, we all don't necessarily see the same thing. Keep in mind, oxyacetylene welding is totally manual. You're the one controlling the torch, you're the one dipping the rod, and most likely, you're the one that has to live with the results. Experiment a little. Try a bigger or smaller flame, and try different size rods until you develop a style and rhythm that works for you. Above all else, keep a safe attitude and have fun with this.